Okay, welcome back. So we're gonna be talking today about formal power series. Now you might say that we already talked about formal power series, but basically what I want to do today is the following. Over the course of the last few lectures, we have used power series a lot, and every time that I do any kind of computation, I tell you, oh, this is in the ring of formal power series, this is not analysis, you don't have to worry about convergence, etc. I wanted to first do some of those computations with power series so that you can see why some of the things that we have done might be suspicious. I wanted you to see what kinds of things we probably should have been worrying about. Okay? And so now, I think you have seen at several points in this class places where you've maybe doubted that I'm telling you the truth, and where it might seem suspicious that we don't have to do analysis. So now that you know what to worry about, today what I want to do is show you why you do not need to worry about it. Okay? So what I want to do is talk a little bit more carefully about what it means to work with formal power series. And just show you a little bit more of the formalism behind the computations that we have been doing. Okay? So throughout today, we're going to let R be a commutative ring. But really, for us, usually R is either the reals or the complex numbers. And so you might as well think throughout all of today that we're talking about the reals or the complex numbers. Okay? So, okay, let me make a definition then. A formal power series is going to be a sequence A0, A1, A2, etc. An infinite sequence like this, where the AIs are in our ring. Okay, so the formal power series formally is just a sequence like this, okay? Which we write A0 plus A1x plus A2x squared, etc. And we might even give this a name, A of x. Okay? But then I want to emphasize that in the formalism, this is just notation, right? It doesn't mean that this is really a function of x. This is just a notation to denote this infinite sequence, okay? And let me show you another notation, which is that we sometimes write, okay, so maybe I'll do it over here, notation. Let's write that an is the coefficient of x to the n in a of x. Okay, so this notation means take the coefficient of x to the n in a formal power series. The nth coefficient is going to be equal to a. Okay. Okay, so this is the definition of formal power series, and now we need to make a ring out of it. So the ring formal power series which we denote R double square bracket of x, has as elements all the formal power series and we need to define operations, right? And so the operations are addition. It's going to be component-wise. So if I take my infinite sequence AN, okay, this is shorthand for this, of course, and if I want to add that to Bn, then what I do is that I just add them component-wise. So the nth entry here is AN plus Bn. N is a natural number. Okay? And the multiplication is going to be like this. So if I would take this sequence, and I want to multiply it by this sequence, then I use the convolution product, where the nth entry here is AN B0 plus AN minus 1 B1 plus etc. up to A0 Bn. Okay? And I let n vary over the natural numbers. Okay? And so, of course, what you should notice is that this is consistent with this notation, power series notation. And what I mean by that is that if, for a moment, we stepped out of the ring of formal power series into analysis, and if this really was some power series that converges in some with some radius of convergence, then if you looked at that kind of power series, then when you add power series, the coefficients are given like this, and when you multiply two power series a of x and b of x, then the coefficients are given like this. Okay? Now, and I should say, always the motivation is that you're really thinking that you're doing operations with this, but then if somebody complains, then you can just back up and say, well, no, you know, I'm not really doing analysis. I'm doing operations in this algebraic ring, okay, in the context of algebra. Okay, so that's the ring. I guess I should also say what 0 is. Well, what is 0? Well, again, you might think in this language, but in this language it's very cumbersome. And really, we know what 0 is. 0 should really be 0 plus 0x plus 0x squared, and so this is 0. We know that. And of course, it's very easy to verify that it does behave like 0. What about 1? Again, it might be less obvious from this notation what 1 should be, but we know what 1 is. 1 really represents 1 plus 0x squared. So 1 is this. And it really is the multiplicative identity, because if you plug in this sequence 1, 0, 0, 0, you're going to find that it is multiplicative identity. Okay. And then there's some kind of easy things that you need to check, right? So you need to check the associativity of plus and of times. You can check the commutativity of plus and times. And you can check the distributivity of times through plus. Okay? Which you should do if you want to show that this is a ring. And again, you know it's going to work out because it's kind of motivated by the formal power series, but the proofs you would write in this language. And so you have to do a little bit of distributivity. So you just check that a times b plus c equals a times b plus a times c. You check it algebraically, and it takes longer to write than to think about what you need to do. Okay? So this is going to be the ring of formal power series, and this is the algebraic object where we are doing all our computations in this class. Okay? Um, I want to point out to you that, so maybe I'll give you some references. So the book, section 1.1 is mostly what I'm going to be following today. And it explains how the ring of formal power series ends up being used in combinatorics. But I also wanted to refer to you to a very nice paper. Even and the paper is called Formal Power Series, I think. Yeah. Formal Power Series. So this paper is a few decades old. It appeared in the American Mathematical Monthly, and it's very readable, actually. And that paper really develops the formalism very carefully. Okay, so if you're interested in looking at that, for example, for the project or just for your own edification, that's a good source to learn about this. Okay? So the next thing that I want to say is this, that again, even though on the book, on paper, we're doing everything formally, and even though there is a formal difference between this and analytic power series and analytic functions, what I want to, the next thing I want to state is this general principle. And I don't call it a theorem because I'm not stating it precisely. But the principle is that any identity of power series which holds analytically say in some radius. So you may do this over the reals or over the complex numbers. It usually doesn't matter too much. If you have an identity which holds in the world of analysis, then and if it's very important, which makes sense for formal power series, then it also holds for power series. Also holds. Formally. Okay. So this is a general principle, and this is kind of the comforting principle behind a lot of our computations. And one could write down the correct hypothesis and say exactly what one means by this, but instead of being so pedantic like that, I think what I'm going to do is just show you several examples of how this plays out and the kinds of things that you need to worry about and the kinds of things that you don't need to worry about. So in the remaining of the class, we're just going to do examples of trying to understand what exactly that means. Okay. And I can even erase this because I think the definition, again, it's just kind of hiding the fact that really we're just thinking about these as power series. So we're just going to do a bunch of examples of this. Okay. So here's an example. A geometric series like this one. For any R in R. Okay. So this is something that you know from analysis. And the idea is that somehow, because this holds let's say when x is less than 1 over r, as a convergent, this is a convergent series that converges to this when x is less than 1 over r. Then this should also hold in the ring of formal power series. But what does it mean for this to hold in the ring of formal power series? So for us, in the formal ring of power series, what does this mean? What does it mean? Well, this is basically talking about a multiplicative inverse, right? So really what this means is that this times this is equal to 1, okay? Where these are two formal power series and this is the identity in our ring, okay? And so how do we prove this algebraically? Here's a proof. Let's consider the coefficient of x to the n in the left-hand side. The coefficient of x to the n in the left-hand side is what? Well, by definition, what you do is you just distribute here, right? I raised the definition, but what you do is that you think, how could I get an x to the n from here and here? Well, I can get it in two ways, either by multiplying this r to the n x to the n times this 1, which contributes an r to the n as coefficient, or I can also get it by using this term times the term x to the n minus 1 here, which would give me an r to the n minus 1 times minus r. Okay. Now, this is only if n is bigger than or equal to 1, right? If n is equal to 0, then you cannot create an r to the 0 and x to the 0 in this way. Okay. So this is if n is greater than or equal to 1, but if n is equal to 0, then the only way of getting an x to the 0 out of this is by going r to the 0 times x to the 0 times 1. And you see then this is 0, and this is 1. And so that means that this is what it needs to be. This is the coefficient of x to the n on the right-hand side. Okay. So this is an algebraic proof of this identity. So that's the first example. Okay, let's look at another example. Let's look at this identity. Sum from n for n greater than or equal to 0 of x to the n over n factorial times sum like this of minus x to the n over n factorial is equal to 1. Okay? This is an identity of formal power series again. So what does it mean? So this means that, well, let's look at the coefficient of x to the n in this times this. Okay. So what's the coefficient of x to the n on the left-hand side? Well, remember, what I do is that I look at the coefficient of x to the k here and of x to the n minus k here in every possible way. So to get an x to the n here, I can get x to the k over k factorial and x to the minus x to the n minus k over n minus k factorial. And I sum for k equals 0 to n, right? In other words, if I were to multiply this out, formally, the coefficient of x to the n would be equal to this thing, the convolution of the a's and the b's. Okay? And so this identity says that this is usually 0 for n greater than or equal to 1, 1 for n equals 0. Okay? In other words, at least this equality it makes sense in the ring of formal power series, and it means this. Now the question is, do we know how to prove this or not? And maybe I'll leave it to you as an exercise to prove that this is true. I mean, this is a combinatorial identity which you can prove. But what we can also do is actually we can invoke analysis. So let me now show you an analytic proof of this identity, which actually gives me a proof from formal power series. So let's give an analytic proof. Well, if this were analysis, then you know that this would be called e to the x, right? So this identity says this is e to the x, and this is e to the minus x. And then you have to remember, okay, when does this converge? Let's forget about this. When does this series for e to the x converge? It converges everywhere, okay? And this one also converges everywhere. And so, this is true. It's an identity of convergent series. And actually, this is true for all x. Let's say in the complex numbers or in the reals. Let's do the reals. So we know this is true. And then let me invoke a theorem from analysis, which says that whenever you have an equality of analytic functions given by two power series, okay, so if you have two power series that represent the same function, for some radius of convergence, then their coefficients are equal. They are equal coefficient by coefficient. This is a theorem from analysis, and actually it's quite easy to prove, because when you have convergent power series, that means that these things are smooth, they're infinitely differentiable, and then you can compute the coefficients, right? What is the coefficient an? Remember that Taylor's formula says you should just take the nth derivative, evaluate at 0. Okay? And you can do that in analysis if you have some radius of convergence. So that means that since we have these two, okay, here's one convergent power series, here's another one, and they represent the same function, then they're equal coefficient by coefficient, and that means that this identity actually holds, and we don't need to prove it combinatorially. It just, we get it for free from analysis. Okay? And so I show this to you so that you realize that even though we always say we do things formally, it's often beneficial to bring in analysis, and you can get free combinatorial identities out of analysis in this way. Okay? So that's example 2. Now let's talk about example 3, or we might call it non-example 1. So let me show you one thing that is true in analysis and is not true for the ring of formal power series. Let's consider the analytic identity e to the x plus 1 equals e times e to the x. This is true in analysis for any x. And so now let's try to convert that into an identity of formal power series. So if we try to translate that into the ring of formal power series, this would say what? Well, let's write this as sum n greater than or equal to 0, x plus 1 to the n over n factorial equals e times sum n greater than or equal to 0, x to the n over n factorial. And that might look okay. Why not? I mean, this does hold true for any real number x, right? But I want to show you that this equation just doesn't make sense in the ring of formal power series. This is perfectly well defined, right? This is a power series where the coefficient of x to the n is 1 over n factorial. But the question is, what does this mean in the ring of formal power series? Put a little warning sign here. What does this mean? Well, what exactly are we doing here? Each one of these individual terms makes sense, and it's a polynomial. I mean, you can just write out x plus 1 to the n. That's in the ring of formal power series. You can multiply x plus 1 times x plus 1 times x plus 1. The binomial theorem tells you what this is. Okay? So each one of these things is a polynomial. Now, what are we doing here? We're taking an infinite sum of polynomials. But that's where the problem is, because we're in a ring where you can add 2 things, you can add 3 things, but you don't necessarily know how to take infinite sums. Okay? That's not something that you do in a ring unless you have some kind of topology behind you so that you can do analysis. And so that's the issue. And let me show you a little bit further what's, if we try to define what is the coefficient of x to the n? Actually, I'm gonna keep doing this in red so that you know that we're in trouble here. This is not gonna turn out to be a valid computation. So what should this mean? Well, we could just say, okay, well, just say that the coefficient of x to the n in this thing is just adding up all the coefficients of x to the n, right? So maybe let me use m. So the coefficient of x to the n here, well, you might say, well, this should just be sum from n greater than or equal to 0 of what's the coefficient of x to the n here? It's n choose m, right? From the binomial theorem over n factorial. Okay. But you see that the trouble is that this is analysis. This is not just algebra, right? This is an infinite sum, and you need to make sense of it. And so we have stepped out of formal power series and into analysis. And so that's what the problem is that we can't really have infinite sums like this. How to deal with infinite sums? We need some kind of topology to allow ourselves to do something like that. And so let me give you the punchline is that it's not going to work. So I'm going to show you how we can deal with infinite sums, and when we're done with that, we will see that actually we cannot deal with this situation. This is not something that lives in the ring of formal power series. So, to make sense of infinite sums, in our ring of formal power series, we need to introduce some notion of convergence. Okay. And the idea, since we want to do things formally, the idea is that convergence should not rely on actual analysis of the reals or things like this. We want some kind of algebraic notion of convergence inside here. And so we're going to say that a sequence of power series converges to some power series f of x if basically what should happen is that when you look at f1 of x, then f2 of x, and f3 of x, the coefficients are stabilizing to the coefficients of this. So what I mean by that is that for any particular coefficient, if I want to figure out what the coefficient of x to the n is here, I want to look at the coefficients of x to the n in these guys, and I want to see them get stuck at a value. And that value is going to be the coefficient here. Okay? So what I want is that the coefficient of x to the any large, okay, so the coefficient of x to the n in any large enough series should always be the same. And it should be the coefficient here. So for any n natural number, there exists some big number n such that this holds for any big enough n. Okay. Does that make sense? Maybe I should just do a quick example of this. I don't know. Let's say that I want to write something that converges to 1 plus 2x plus 3x squared plus 4x cubed, etc. And so what I want is that maybe f1 gets every coefficient wrong. Okay, maybe f1 is, I don't know, 3 plus 7x plus 9x squared and so on. Then f2 gets maybe the first coefficient right, but then the other ones are whatever other thing. Okay? And then maybe f3 gets the first two coefficients right, maybe even the third one, and then it gets the next one wrong, and so on. And then, I mean, the point is that, I don't know, here maybe you get all of these right, and then you fix the next one, but maybe you get the next one wrong, and so on. But the idea is that for any particular coefficient, like this 2, eventually you're going to see that the coefficients here are always equal to 2, right? And this is not that these should converge to 2. You want them to actually be equal to 2. What you will see in that case is that when you write these infinite sum, when you try to define the infinite sum by looking at the partial sums, you're going to see that the partial sums, coefficient by coefficient, they converge in the sense of analysis, but they don't stabilize the way that they do here. So this is what it's going to mean for us to have convergence. Okay. Now let me define the degree of a power series be the smallest n such that the coefficient of x to the n is not 0. Okay? And so here's an easy proposition. If I want to define an infinite sum of power series, like this one, well, how would I define it? I would say, well, let me look at the partial sums. A1 of x, then A1 of x plus A2 of x, then A1 plus A2 plus A3, etc. And I would want that to converge in this sense. Yeah?
So, quick question. This is sort of like the opposite of the degree of a polynomial, right? Where you're looking at like the biggest n, usually.
Yeah, that's right. So this might seem a little bit strange because this is the opposite of the degree of a polynomial. This is the smallest exponent that appears, not the biggest, because there's probably not going to be a biggest one that appears. Okay, so where does this converge? Well, imagine that these were partial sums of something. So this was A1, A1 plus A2, A1 plus A3, plus A2 plus A3, A1 plus A2 plus A3 plus A4. That means that AI would be the difference between this and this, right? And you would find that it has a lot of zeros. It starts with a lot of leading zeros, and the further down you look, the more leading zeros that you have. And so to make that precise, really what we need is simply that the degrees as you increase, the degrees go to infinity. Okay. And again, let's look at it here. So what is the degree of A2? Well, A2 is this minus this. So the first coefficient is not 0, so the degree of A2 is 0. The degree of this minus this is 1, the first place where these are different. The degree of this minus this is 3. Right? And so the idea is that these degrees should increase to infinity. And if they do increase to infinity, then it's kind of clear that these numbers stabilize in the way that they should. Okay. So this proposition is actually, when you sit down to write a proof, that it's fairly simple. You just have to kind of think about it and it's not a terribly deep proposition. Okay. So, for example, to go back to our warning for what can go wrong here, does this converge? Well, here's an infinite sum. What is the degree of this term? Again, you have to think degree in terms of power series, not a degree in terms of, not degree as a polynomial. And this guy has, the first coefficient is always non-zero, so this guy always has degree 0. So degree of x plus 1 to the n over n factorial is always 0, because the first term is always non-zero. So this sum is not convergent. So this infinite sum is not convergent according to the topology that we just introduced. which is why we can't make sense of this as an identity in the ring of formal power series. But sometimes, I mean, we actually will be doing a lot of infinite sums. We just have to make sure that they're properly defined. Okay. Let me.
So again,
Yeah.
just to be clear, so this x plus 1 to the n over n factorial. Now you're thinking of that as like a power series in its own right, rather than somehow like the term of a different power series.
That's right. So here, if I try to make sense of what this infinite sum might mean in the ring of formal power series, then this would be an infinite sum of power series. And so I'm regarding this term as a power series, and it is in that sense that it has degree 0. So that's why we cannot make sense.
Okay, and so if you were just looking at like x to the n over n factorial, that degree would be going to infinity, because that's also a power series, but it just has one term, right?
That's right. So I mean, maybe let's okay, I think I had written this down and then I erased it. But for example, can we make sense of this? I'm gonna write something here. So let me. So what if I think of this as an infinite sum in the ring of formal power series? Actually, yeah, maybe we could even like. Let's even get a little bit. Let me write something a little bit more complicated. Okay. Let's say I'm asking myself whether this makes sense in the ring of formal power series. So what I have to do, to see if this makes sense, is I have to look at this guy and see if the degree of it goes to infinity. But what is this? Well, we know what this is, because this is a geometric series, so this is 2 to the n times x to the n plus x to the n plus 1 plus x to the n plus 2, and so on. And so this guy, I'm going to do it in green, has degree n, which, as n goes to infinity, the degree does go to infinity. And therefore, this is well defined as an element of the formal power series ring. Yeah, that's a very good question. So this is what you want to watch out when you write down infinite sums. You want to make sure that it looks like this and not like this. Okay, so we have been actually, if you look back at your notes, you'll see that we have been doing infinite sums in this class, and if you want to be extra careful, you should look at the notes and see that I never lied to you. And every time when I prepared class, I thought about this and I saw, okay, yes, every single time this is fine, this works out. In the last couple of classes, we actually started talking about infinite products, which is more worrisome. We did this in the context of partitions. So I want to extend this proposition to infinite products. Okay, now there's several tricky things about infinite products. Okay. For example, one thing that I actually want to do to make this statement is that I want to write my infinite products like this. So I want every factor to be 1 plus higher order terms. Now, why is it that I want to do that? because if you're looking at an infinite product, and if you allow this number to be other than 1 infinitely many times, let's say, then the leading coefficient is already going to be an infinite product of things, and you don't really want to deal with that. Whereas if finitely many leading coefficients are not 1, then you can just kind of divide by those constants, and that's fine. But so when I do infinite products, it just happens naturally that there's a 1 there whenever you want to do this. You'll see in practice that these things always start with 1 when you actually want to do this. And again, what does it mean for this to converge? Well, you just take the partial products, and those make sense because those are finite operations. Now, I want to make clear that here, this has degree greater than or equal to 1. So it turns out that the condition is exactly the same. And the proof is basically as simple. This is not a terribly deep fact. Okay, so let's do a couple of examples. Where was I? Example number. Let's say that you have two power series, and you want to define this. How would you define it? Well, you would define it formally, just the way that you would do. Just plug in, right? So if f has coefficients little f and g has coefficients little g, then you would define this to be sum for n greater than or equal to 0 of fn, and then you just plug this in, right? So sum m greater than or equal to 0, g m x to the m, and you raise that to the n. Okay. Now the question is this well defined or not? Well, it's an infinite sum, right? So what do we need? We just need to check that the degree of this thing increases. Okay. Now, what is the degree of this to the n? In other words, what is the lowest power of x that appears here? Well, there's two cases. If there's a constant here, if this thing starts constant plus blah, 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 then when you raise that to the n, you're still going to have that constant. Right? But if you don't have a constant, let's say if you start with x cubed, then when you raise that to the n, then you're going to start with x to the 3n. And that goes to infinity. And so this makes sense if and only if you don't have a constant. So if the degree goes to infinity, if the constant here is 0. But if the constant is not 0, then this doesn't make any sense. It's what happened here, right? E to the x plus 1. That's the composition of e to the x and x plus 1. And the trouble is that x plus 1 has a constant. So, but I can define e to the 2x, that's fine, or I can define e to the anything that doesn't have a constant, that's fine. So this I can do as long as G0 is equal to 0. Okay. And then this is the ring of formal power series. Okay. And so again, what this means is that in the ring of formal power series, you should feel free to use compositions wherever you want. But whenever you use a composition, you just have to be careful that the leading coefficient is 0. Which again, you'll find in practice when you want to do this in combinatorics, it always is 0. And checking it is very easy because you just look at the first term. All right. So that's that. Let's talk about a different example. When did we talk about infinite products? We did this when we were talking about partition identities. So I'll remind you that we showed that if we looked at the formal power series of partitions of n whose parts are less than or equal to k, then we saw that this was equal to 1 over 1 minus x times 1 over 1 minus x squared times 1 over 1 minus x to the k. Okay. And then I just kind of waved my hands and said, that it followed that if I did not restrict the size of the parts, then I just got this infinite product. Okay, so how can I actually make this argument correct? Well, oh, I forgot my x to the n here. And here I should have this. So the proper way to make this argument is to say, well, I already proved this for any particular value of k. And then what I'm going to do is I'm going to take the limit as k goes to infinity of both sides. Okay. So here really I took limits as k goes to infinity. Okay. So what do I need to do to ensure that this makes sense? Well, again, this is limited in terms of formal power series. So what I should check is that as k gets bigger and bigger and bigger, the coefficients of this guy stabilize to be this. Okay? Well, you see, the thing is that if, I don't know, let's look at the coefficient of x to the n. Right? So here, it's the number of partitions of n with parts less than or equal to k. And I'm letting k get really, really big. Right? Well, if you have a partition of n, you cannot use parts that are really, really big. You have to use only parts that are less than or equal to k. And as soon as k is bigger than n, you're never going to use a part bigger than n, and this is going to be equal to this. Okay, so for each particular coefficient, you find that these numbers, as k grow, stabilize to this number. So this really does converge to this. Okay? So that's why the left-hand side converges to this. Now, what about the right-hand side? Well, here, the question is whether this product makes sense. If it makes sense, then by definition, it's the limit of these things, right? So why does this make sense? Well, it's an infinite product, so I should check that the limit of the degrees goes to infinity. But again, what is the degree here? Well, this is 1 plus x, etc. This is 1 plus x squared, etc. 1 plus x cubed, etc. You forget the 1, because you're supposed to take it out. And then the degrees go 1, 2, 3, they go to infinity. So therefore, this thing is a well-defined infinite product, which by definition is the limit of these things. And so that's really how you carefully go from here to here. But again, as you practice with this, you learn that these things work out and that you can just make the argument. I don't know, if you see this written in a paper, it's usually not even mentioned that this is really what was behind the scenes. But it's important that you know that this is really what was behind the scenes. Okay, let me prove a little proposition that's important. If R is an integral domain, remember that means that there's no zero divisors, then this is also an integral domain. Okay. Again, remember that integral domain means that if A and B are not zero, then the product is not zero. Or equivalently, if a product is equal to zero, then one of the factors has to be equal to zero. Okay. I think because I'm running a little bit short on time, I'm going to let you prove this, which is a fairly simple algebraic exercise. Right? This is algebra. This is about the ring of formal power series. But I want to show you how we use this. We actually have used this already in class. So remember that we were studying the Catalan generating function. The generating function for the Catalan numbers. We showed that it's satisfied x c of x squared equals c of x minus 1. Okay. Remember we had this combinatorial recurrence that said that Cn was the sum of Ck times Cn minus 1 minus k. And then through some manipulations we saw that that was equivalent to this identity. And then what we did is that we just used the quadratic formula to solve for c of x and to find the coefficients which were the Catalan numbers. So I want to do that a little bit more carefully now. So I'll do the same thing but a little bit more slowly. Or at least minding maybe more quickly, but minding the right details. So if I multiply times 4x, I get this. And I do that so that I can complete the square here. So I get this. Okay? And so then I said this is this square. I justified in saying that, well, yeah, because this is a ring, and in a ring you can multiply this and get this. And then I talked about taking the square root of 1 minus 4x. Okay, well, what does that mean? Well, we can make a definition. 1 plus x to the r equals sum of r choose n x to the n. When greater than or equal to 0, when r is any real number. So again, this is just notation. This is a well-defined power series. I can put coefficients. That's fine. I just denote it like this. But the good thing is that in the back of my mind, I know that this is an identity and analysis, which means that the equations that analysis gives us are going to hold here as well. So from analysis, we get the usual equations like 1 plus x to the r, 1 plus x to the s is equal to 1 plus x to the r plus s, or 1 plus x to the r, and then I raise that. Well, again, because I can now use this to define 1 plus anything to the r, as long as that anything has no constant coefficients, as we just talked about. Right? Because we can do composition. Instead of x, I could put in any function that doesn't have an independent coefficient. Which means 1 plus x to the r, well, that's 1 plus something, and so I can raise that to the s, and I get 1 plus x to the rs. So that means that actually I can say that this is 1 minus 4x to the 1/2 squared, where this is defined from this. Okay, well now this is a of x squared, this is b of x squared, and now I want to take the square root, but I have to be a little bit careful. So I factor it like this, right? That's just an operation in the ring. And now this is where I'm going to invoke that this is an integral domain. And we're doing all the computations over the reals, which are an integral domain. So this is an integral domain, and therefore a of x is equal to plus or minus b of x. Okay? In other words, let me just substitute 1 minus 2x c of x is equal to plus or minus 1 minus 4x to the 1/2. Okay. I don't know right away if it's plus or minus, but a moment's thought will make me realize that 1 minus 4x to the 1/2 starts, if you look at the independent term here, it's a 1. 1 plus anything to the r always starts with a 1. So if this has a 1 and this has a 1, then the sign must be the plus sign. So because of this one and this one, I get that the sign has to be the plus sign, and therefore I get what I got, which is that c of x is equal to what? Is equal to 1 minus 4x to the 1/2 over 2x. And then remember I took that and I expanded this using this formula, and I figured out the coefficients, which were the Catalan numbers. But you see, it was very important to have that this is an integral domain to carry out this computation. But again, the moral of the story is that in retrospect we might have worried, but in the end the story is usually that actually we were fine. The story was always that in the end everything that we did was correct. Let me just conclude by talking about how we can do calculus in this ring. Okay. Now, calculus, normally we start calculus by defining let's say a derivative, and the derivative is given by a limit, f of x plus h minus f of x over h as h goes to 0. But it's going to turn out actually that we're going to just do this in a very algebraic way, and we're going to just remember that everything that analysis tells us, as long as there's a radius of convergence, we can just kind of steal it. But a lot of the operations just work out formally. Okay? So we can define what is the derivative of a n x to the n. Again, the trouble is that if you try to define it in the way that calculus would define it, limit of plug in at x plus h minus limit of plug in at x over h, you're going to find that that is not convergent in here. So the old calculus definition doesn't work, but we kind of know what we want this to be, right? We just want this to be, it's like what our students would do. In calculus, they just bring down the n, etc. That's what they always do, and that's what we're going to do. So what's the coefficient of x to the n? It's n plus 1, a n plus 1. Okay? And that's going to be our definition. And it's well defined because this is an element of the ring of formal power series, right? It's a formal power series. Well, of course, the definition is only as good as it is useful, and so you need to check certain things. For example, that if you take the derivative of a plus b, then that's going to be just the individual derivatives. That's clear from the definition. We want this, we want the product rule, right? How do we prove this? Well, here it's not clear that we can rely on analysis because we need to prove this for any elements of the ring, and so here you just have to kind of get your hands dirty, just compute what the coefficients of this are, compute what the coefficients of this are, and you're going to find that the product rule holds. Or similarly, whenever this is defined, right, when b of x has no constant coefficient, you're going to find that the chain rule also holds, etc. Okay? And so that means that, again, we can take identities from analysis, and through this algebraic operation of taking the derivative, we're going to find that the same identities hold. So, for example, let's back up what example I mean, maybe 7. Say that I have this. Okay. Well, we know what. If this was a course in differential equations, then I hope you have some urges to do something here. And the point is that we can do the same things here. So Of course, in differential equations, you would say, well, this is the derivative of the log of f of x. Okay, well, is it? Here we didn't do anything. Is this true? Well, first of all, we have to think of whether this even makes sense. So, for example, does log of f of x make sense? We're doing. So, how do we define the log of something? Well, we define it by its power series, right? This is what we usually use. So, the log of 1 plus x is equal to, or is it 1 minus? That's it. Is that right, or do I have the signs off? Kind of. That's right. It's been a little while. Yeah, this is right. Okay, so this is the identity from analysis, but now we can just define the logarithm like this. Right? Again, we just take this power series and we define it. We call it the log of 1 plus x. So what is log of f of x is? Well, the thing is that f of 0 is equal to 1, which means that f of x is equal to 1 plus other things, which means that I can plug in f of x here. F of x is 1 plus some stuff, and so again I can do composition, and here I will get something. This would be the definition of this. Okay? And so to prove this, what do I need? Well, this is an instance of the chain rule. I just need to make sure that the derivative of logarithm is what I think it is. So how do I make sure that the derivative of logarithm is what I think it is? Well, because actually now it's easier to take derivatives, because the derivative, you just do the formal process of bringing down, this disappears, this is again minus 1, then this 2 cancels this one, so I get the right thing. So the logarithm of 1 plus x is 1 over 1 plus x, and then here I'm just applying the formal chain rule, which holds for formal power series. Okay, so this is fine to get from here to here. Now, what would be the next step that we would do in differential equations? We would say, okay, well, if two things have the same derivative, then they're equal up to a constant. Is that true? Sure, because you see, the way that we define the derivative, you can recover each coefficient of the derivative. Sorry, from the derivative, you can recover each coefficient of the original function except for a sub 0. For the other ones, you can recover them. So that means that you can recover the coefficients of both sides. They're equal except for the initial coefficient. Okay? And again, you can just see because of comparing independent coefficients, you're going to find that c is equal to 0. Kind of plug in x equals 0, but we're not really plugging in x equals 0, we're just comparing the initial coefficient. Here it's 0, here it's 0, so therefore c needs to be equal to 0. So therefore g of x is equal to the log of f of x, or f of x is equal to e to the g of x. And so you can take differential equations and bring them into the ring of formal power series, and they become an algebraic version of the theory of differential equations. And you can use that power to do computations here. So it means that you can, it's not exactly calculus that you're doing, it's kind of an algebraic analog of calculus, but it works out, and you have it at your availability to prove things. Okay? So this is an overview of the ring of formal power series. Again, the moral of the story is this. The moral of the story is don't worry about it too much. Just check for the obvious things that could go wrong. And but in practice, you're going to find that the things that you're trying to do with combinatorics the formalism doesn't get in the way, and you're able to prove the things that you want to prove. Okay. So there you go. That's what formal power series are all about. And again, if you want to read more, this is a combinatorial treatment that more or less says what I said today. And this is a more algebraic treatment of how you actually prove things in there. Okay. Cool. See you guys next time.